Okay, complex numbers continued. Okay, so last time we defined what a complex number. Ooh, there we go. We defined what a complex number was. It's complex numbers in the form a plus bi, where a and b can be any real numbers. So it's the complex numbers are built from real numbers, but just attaching that letter I to the real numbers. So where a and b are real numbers, and I is equal to square root of -1, which equivalently we can say I squared is equal to -1. And that's that special number that allows us to branch out beyond the real numbers and let us talk about things where we have negatives under a square root. So we talked about, now I'm summing up last lecture, so I'm not going to like enumerate these examples. I'm just going to quickly talk about what we did last time. We took negatives that were under a square root and we said, oh yeah, we can deal with those. We can deal with those by first taking the negative off, and I'll skip the steps here because we talked about this last time, but just reminding you, the power that I has here is it basically allows us to say, okay, if there's a negative under a square root, we could just call that negative part, we just call that I, and then we deal with the square root like we normally would. So in this case, this would simplify to 4i square roots of 3, just simplifying the square root of 48 like we did in 0.4. Okay. Maya says, you can't hear me. Can you, let me make sure my mic is good. Can everyone else hear me? How's that going? Maya, can you hear me now?
I can hear you.
Okay. So it might just be you, Maya. Maybe. Let me chat with her because she can't. Oh, maybe she can hear me now. Let me see. Okay, good.
My speaker wasn't on.
Oh, okay. Okay. No problem. Okay, so we talked about this part of I. What else did we say? We also said that for a number like 4 plus, 2i, that we call 4 the real part and 2 the imaginary part. That's just some, kind of vocabulary here. If I refer to the imaginary part of the number, I'm talking about the number that's attached to I. And 4 is just the normal old real number. Okay, so we talked about this last time. I also, briefly at the end, talked about how the powers of I are cyclic in nature, meaning that another way to describe them is recursive, meaning that they repeat. That's fancy words for saying the powers of I start to repeat. But I did that last time, and it's honestly not important enough for me to reiterate here. So let's keep going from here, and let's talk about, now this next part is going to be very nice and intuitive, and that is arithmetic. And by the way, arithmetic means the 4 fundamental operations. Arithmetic with complex numbers. All right. And I'm just going to run 4 examples. We'll do one of each. Actually, we will skip division because wait, should we? Yes, I think we will. We'll come back to it if we have time. Okay. Oh, shoot. I'm sorry. Give me 1 second. I'm supposed to have a delivery today. And I think they just got here. That is horrible timing. I'll be right back. I'm sorry about that. Sorry, I'm in class right now, so I'm. No, you're good. I'm just saying. All right, you need this problem. Okay, thank you. Okay. All right, I apologize for that. I'm having a window delivered from Lowe's, and of course they pick right when I'm in class to deliver it. All right, example 1, we're doing addition. So let's consider 2 plus 3i, and we'll wrap it in parentheses just to emphasize that's one complex number plus another one. And just to make it interesting, let's throw in some negatives. -4 minus I. How do we add these? So if I just gave you this and asked you to add these, a lot of you would probably end up getting the problem right, even without knowing really what to do, because the thing we're about to do is I think, very intuitive. It makes sense for how you know to deal with adding like terms. It's going to come down to like adding like terms. We're going to add the real parts, so 2 plus -4, and then plus 3i plus that -1i. And that's going to give me the real part, so 2 plus -4 is -2. And then 3i plus -i, that's the same as like 3 plus -1, because that's a -1i, right? 3 plus -1 is 2. And there we go. So addition works. It's like as if you attached a variable, right? As if it's like an x. 2 plus 3x plus -4 minus x. It works the exact same way. So nothing crazy going on here. Any questions about that one? Okay, let me make sure we note something here, that 3i plus -i is the same as 3i plus -1i. So don't forget, when it's just an I written, we understand that there's a 1 there. And if it's a -i, we understand it's -1i. So this is the same as having, it's kind of the same as having 3 plus -1. Not exactly right, because you still got to attach the I, but 3 plus -1 is just 2. Hence the answer for this part is 2i. A lot of people forget that, and they want to say, oh, 3i plus -i, the i's cancel and I just get 3, right? But that's not true. That's not how that works. It's more like this. Okay, let's move to subtraction. Let's do 2 plus 3i. We'll just do the same ones, but we'll subtract them. Minus -4 minus I. So we're going to change this into an addition problem, and then we're going to use our addition rule. That's all we're going to do here. So we're going to say, if I distribute the minus sign to both of these, I'm going to have 2 plus 3i in parentheses, and then plus, and I'll distribute the minus sign to both of these in here, which is effectively going to flip both of the signs in here, 4 plus I. Now that I've written it as an addition problem, we can do exactly what we did up here. Add the real parts, 2 plus 4, and then plus 3i plus I. And that's going to give me 6 plus 4i. 2 plus 4 is 6, 3i plus 1i is 4i. Okay, let's do another subtraction one so you can see what I did there again. And so let's, how about we call that number A, or part A rather, and let's call this part B. Let's do 7 plus 2i minus 6 plus I. Okay, first thing, write it as an addition problem. So 7 plus 2, the first one doesn't change. And then we write plus, and then we're just going to distribute the minus sign to both of these inside the parentheses, which is changes this to an addition problem. So instead of minus 6 and minus I, it's going to be plus negative 6 plus negative I. So flipping the signs on both of these numbers in here. And now adding the real parts, I'm going to have 7 plus negative 6. And then positive 2. So the positive 2i, the reason there's a plus sign there is because that 2i is positive. So 2i, positive 2i, plus that negative I. 7 plus negative 6 is 1. 2i plus negative I is I. There we go. Okay. Any questions so far? All right. Let's move to multiplication or products of complex numbers. So example 3, and I'll do 2 of these as well. Example 3a, let's say 2 plus 3i multiplied by, what was the first one? Negative 4 minus I. So this is a complex number. This is a complex number. Let's take their product. What happens here? Well, we know how to take products of a 2 by 2, right? We distribute. We distribute this term to this and this term to this, so that's first. So first I'm going to have, let's see, here I'll write it out for you so you can see what's going to happen here. I'll draw a nice little representation of what's happening here. So 2 gets, oh crap, I wrote it down wrong. 2 plus 3i, negative 4 minus I. All right. So the 2 is being sent to both of these. So we distribute the 2 to both of them. And we're getting, I'm going to write it over here. 2 times negative 4 is negative 8. 2 times negative I is negative 2i. Okay. And now moving on to the next term, 3i is now going to get multiplied onto both of these. 3i, here we go, let's see, okay, all right. 3i times negative 4 is negative 12i, just multiplying the coefficients, 3 and negative 4, gives me negative 12 and just attaching I. Now 3i times negative I, well, it will be negative, 3 times negative 1, right? And then I times I, there's product of 2 i's here is just I squared, okay? I can combine some like terms, negative 2i minus 12i, negative 2i minus 12i here. Those are like terms, right? They both have a single I attached, and negative 2 minus 12 is negative 14. Now, what about I squared? I'll do it in the next step. I squared is equal to negative 1. So recall, I squared is equal to negative 1. So I've got negative 8 minus 14i minus negative 1, just replacing I squared with negative 1 there. It's doing exactly what I wrote over here. If I squared is negative 1, here we go. So I'm going to have negative 8 minus 14i plus 1 here, because I subtracted an I squared, and I squared is negative 1, so it turns into a plus 1. Negative 8 plus 1, those are like terms now, right? They're far away from each other, but those are like terms. And negative 8, so that's a negative 8, and a positive 1 is going to give me a negative 7. So the point is my answer should be back in the form like a plus bi. I should not have extra stuff hanging around. After I multiply and you do all the simplifying, you should have a real part and an imaginary part. No extra numbers. There should not be 3 terms, just 2 terms. Real part, imaginary part. Okay. And this whole I squared business, that's going to happen every time where you end up with an I squared that you've got to simplify when you're taking products. So let's take the product part B here. Let's say, let's do a more interesting one, like 3 minus 2i times 6 plus 4i. Okay, you guys try that for a second on your own while I go check and make sure the delivery guys don't need anything from me. I'll be right back. Emil, where's is she in here? All right. Okay. All right, sorry. Okay. Hopefully you tried this. Let me get caught up with y'all if you're already multiplying. So I'm going to send the 3 to the 6 plus 4i. So I'm going to have 3 times 6 is 18. 3 times positive 4i is positive 12i. That's the first part. Now here I'm sending negative 2i to both of these, so I got to keep in mind that I'm multiplying a negative 2i on both of these. Negative 2i times 6 is negative 12i. Oh. Okay. And then negative 2i times 4i is negative 2 times 4 is negative 8. I times I is I squared. Okay, cool. Now, it just so happens, I didn't even plan this. I must have picked, that's fine. Yeah, so what's going to happen here when I combine my like terms is these cancel out, so I'm left with 18 minus 8i squared. But remember, I squared is just negative 1. So I can replace I squared with negative 1 here. 18 plus 8 now in my next step, and finally I'm getting 26. And that's fine. That's fine. The point is, it's still technically in complex number form, right, where the real part is 26 and the imaginary part ended up being 0. It zeroed out, right? The point I was making last time with this previous problem is that you should never end up just having 3 terms left, right? You should have 2, or in this case 1 term left over. You could have 0 too if everything zeroes out, both the real and imaginary part, but just make sure you're getting that last step of dealing with the I squared. And the reason I'm making a big deal about it is because students forget all the time. Like I'll have on an exam, like I might put part A here, and I'll have a lot of students stop right here at this step and leave that I squared in there. But you've got to keep going, get rid of the I squared, finally combine those last like terms. All right. Okay, that's arithmetic. I said we would talk about division later, so yeah, I'm going to stick to that. Let's put a pin in that. We'll get to it if we get to it. But what we really need to get to today is looking at complex numbers as solutions, complex numbers as solutions to quadratic equations. So remember in 1.4 we were looking at quadratic equations, generic quadratic equations, ax squared plus bx plus c is equal to 0, and we can solve for x very quickly, but well, quickly, right? It depends on how bad the problem is, but we can use the quadratic formula to solve quadratic equations. Okay, no problem. We did that last time, or the past 2 times, really, in section 1.4. But we also noted that there are times when the discriminant is less than 0. When the discriminant, remember, that's the discriminant, is that fancy term, discriminant, is the fancy term for b squared minus 4ac. That term, that part under the radical. When the discriminant is less than 0, but what does less than 0 mean? Negative, right? That's what I'm saying. It's a fancy way of saying negative. Then we do not have real solutions because the real numbers do not allow for negatives under a square root. What we will have is we will have complex solutions. So let's look at some of those. We will have complex solutions. Now here's the nice thing. All the work we're about to do setting up the quadratic formula, it's going to look the same as it did in 1.4. So example, this would be 4, right? Yeah, example 4. Example 4, solve, okay, let me go to the book because I had some in mind. Which ones did I give y'all? I don't want to use any of those up. X squared plus 3x plus 7 is equal to 0. All right, first thing you want to do when you look at a quadratic equation like this, you see, oh, look, it's got a leading coefficient of 1. My first instinct is let's try to factor it. Okay, that's a good first instinct. Let's try to factor it. You look at, okay, think of 2 numbers that multiply to give 7, that add to give 3. No way to make that happen, right? No way to make that happen. It's not factorable. Okay. Once you're there, it's not factorable. What do? You fall back on the quadratic formula. So you'd say, and I'm going to write the solution part in red here. We say x is equal to, ooh, wait, before we do that, let's name a, b, and c. A is 1, right? That's the leading coefficient. B is 3. That's the linear coefficient there attached to the linear term, the middle term, you can say. And C is 7, that constant term. All right, now I'm ready to fill in that quadratic formula. So negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Okay, let's start cleaning it up. I'm going to have negative 3 plus or minus square root of 9 minus 28 all over 2. All right. So 4 times 1 times 7 yielding that 28 there. 3 squared is 9 and 2 times 1 is 2. That's all I've done. That's all I've done so far. Okay, I'm going to keep working here. Negative 3 plus or minus square root. What's 9 minus 28? By the way, it's all over 2. What's 9 minus 28? That is a negative number, a negative 19. Negative 19. And then we say, this is where we know, okay, what do we know at this point? There are no real solutions to this. There are no real solutions to this. But we do not just stop and say no solutions. We say there are complex solutions, right? And how do we show that? Well, we deal with this little square root of a negative number by pulling the negative out and calling it I. So we say negative 3 plus or minus I times square root of 19 all over 2. Okay, we've effectively gotten rid of the negative under the square. Well, we haven't gotten rid of it. It's still there, but we've rewritten it with the I taking up the taking the place of the negative under the square root. And just as a quick reminder, how does that, what's the justification for from that to that? Remember that square root of negative 19 is the same as square root of negative 1 times 19. That's the same as square root of negative 1 times square root of 19 by splitting the radical around the product. But square root of negative 1 is just I. There we go. So that's the long story there. Now your last step here is you should just look for, can I simplify this at all? Can I can I simplify square root of 19? No, right, I can't. It's prime. It has no perfect square factors, and I can't do anything else. There's no simplifying to be done here. Okay. Let's look at, that was that one. All right, let me see. I'm trying to find another good one. Okay. Example 5. Solve. Oh, I lost it. Where'd it go? Oh, there it is. 2x squared minus 2x plus 1 is equal to 0. All right. So first thing you want to do when you're trying to solve one of these is you see if it can be factored. It cannot, right? And maybe you're thinking, even if it can be factored, I know that if I'm going to factor this, I would have to use the grouping method because the number here is not a 1. And if you're like, I just hate the grouping method, right? Well, you can still use the quadratic formula. You can use the quadratic formula for any quadratic equation, as long as it has rational coefficients, or integer coefficients, but we're not, don't worry about that. So but for the context of our class, you can solve any quadratic equation with the quadratic formula. So let's do that. Let's name our A, B, and C. Okay, A is 2, B is -2, C is 1. All right, x is equal to -b, so that's going to be negative b, there's my b, plus or minus square root. Notice how every time I'm doing this, when I first write down everything, I'm not trying to think ahead and be like, okay, negative and negative makes a positive and stuff like that. I'm just writing it all in, not trying to do 2 steps at once as I'm writing it down, right? I feel like that's just a good rule there, because then if you're going back and you're checking your work, you're like, okay, when I wrote it down, was I dealing with the negative all at once, or was I, it's much better to just get the formula down with everything explicitly plugged in without doing any simplifying yet. Now in your next steps, now you can do, as much as you feel comfortable with all at once. -2 squared is going to be 4. 4 times 2 times 1, by the way, minus, right? Minus. 4 times 2 times 1 is 8, all over 4. Okay, that's going to be 2 plus or minus 4 minus 8 is -4, all over 4. So arithmetic, right? Don't just look at this and be like 4 minus 8 is 4, right? No, it's not 4, right? It's -4. Okay. All right, now we have 2 plus or minus I times the square root of 4, all over 4. Okay, just dealing with that negative under there. Now, square root of 4 simplifies all the way to a whole number, right? So now I'm getting 2 plus or minus, I'm going to say square root of 4 is just 2, right? So I'll say 2i, because remember when it simplifies to a whole number, we like to write the number on the left of I. Now, since both of these have a 2, I can factor a 2 out. And why would I want to do that? Well, because 4 has a factor of 2 as well. So what I'm saying is I can clean this fraction up a bit by doing this. Factor a 2 off of the numerator. So instead of 2 plus or minus 2i, I'm pulling a 2 off of both of those, so but they're both going to just turn into 1s. So 1 plus or minus 1i. Okay. But this 2 can cancel partially with the 4 in the bottom, or partially cancel that 4 in the bottom. The 4 in the bottom will turn into a 2, and I'll be left with my numerator, 1 plus or minus I. That's it. These are the two solutions, 1 plus I over 2, 1 minus I over 2. And by the way, sometimes if you like look up as you're doing the problems I gave you for 1.5, or if you decide to do even more, or in the homework or whatever, if you're seeing solutions like this, 1 over 2 plus or minus I over 2, this is the same thing. They're just splitting the fraction. That's all. It's the same thing. So just in case you see that, if you're, practicing and you're checking your answers on Mathway or whatever, Wolfram Alpha or whatever you use to check your work, if you see something like that, it's the same. These are the same thing. Now, I want to make a note about these solutions, about complex solutions. Okay. This is just to help you out. Always come in pairs. What do I mean by that? Well, consider example 4, where from example 4, our solutions were x equals -3 plus I square root of 19 all over 2, or x equals -3 minus I square root of 19 all over 2. In example 5, the solutions were x equals 1 plus I over 2, or x equals 1 minus I all over 2, right? Those were our solutions for example 4 and 5. And as I'm writing them here, I'm just splitting them instead of just writing plus or minus, right? It's just to emphasize the fact that they're coming in pairs, where the only difference between these solutions is the little sign in the middle, the sign on the real part. The sign, no, sorry, not the real part, the imaginary part. The sign on the imaginary part, it is flipped. Okay, just to note, it's just like a little helpful thing to note. There's more to say here. I'm kind of glossing over it a little bit, but yeah. So if you're writing out two solutions explicitly, like split like this, then they should, in their complex, they should look very similar. They should look exactly the same, except the little sign in the middle. Everything else is the same. Like, look at these two. They're complicated, right? But everything is the same between this and this. A -3, an I, a square root of 19, a fraction bar, a 2. Everything's the same except for that little sign in the center. And same here. It's easier to see here because these are more simple solutions. All right, so that is all I want to do for section 1.5. So at this point, I can, well, we can review. So I gave you all the problems I wanted you to look at for review last time, and I've got my little list here. So you guys let me know what you want to look at from the review that I gave you. Remember, there are 1, 2, 3, 4, 5, 6, 7 sections. 7 sections. So 0.4 is rational exponent stuff. 0.6 was factoring. 1.1, what was 1.1? graphing things in two variables, so mainly like x and y intercept stuff, maybe graphing a circle. That was getting, oh no, that was 1.2, sorry. 1.1 was just getting acclimated to the coordinate plane, right? The whole quadrant, the 4 quadrants thing, also distance and midpoint. 1.3 was lines, so line equations. 1.4 and 1.4 was all about quadratic equations. And 1.5 is complex numbers, and also coming back to quadratic equations at the end of 1.5, which is what we did here with these 2 examples. So what do y'all want to look at? What is the section that you would like to consider? Oh, while you're thinking, while you're looking at the problems I gave, that I listed out for you last time, or not, it was like Monday, I forget when I did it, but I gave you all the review problems, so as you're looking at those and deciding what you want to go over, let me just remind you that exam 1 is on February 8th at when is this going to be? 12:30 p.m. in room. It's in Ayers Hall, room 3. I believe it's 355. I'm going to triple check. 355, and so it's in person. No, unless you've got some reason, which I believe I know one of y'all did. I forget, but I know we've already talked. If you need to take your Aviana, yeah, if you need take your exam remotely, we've already talked about it. That's fine. So this doesn't apply to you, right? So any questions about review? Or questions about the exam itself? What do y'all have? Yes, Kimberly, go ahead.
Can you kind of go over the first section that we did, the rational exponents, just to kind of clarify and review it?
Yeah, let me see what I assigned for that and see if those questions are kind of a good way to sum it up. If they're not, I'll pick more. So let me go to my book. 9 and 10 were the problems I talked about there. Yeah, they're that's okay. All right, so 0.4, or I think WebAssign calls it 0.4 and the book calls it P4, whatever. That's that section. Number 9 and 10 give you they say here's a radical expression, and is that really all I gave you for that? Yeah, I guess so, yeah. And then write its corresponding exponential expression. Okay. So number 9 says 1 over square root of 3. So it's exponential expression. So I'm trying to get what I should have. What I should have is the number under the radical 3 raised to some power. Now, would it be positive or negative? Well, since the 3 is in the denominator, I should have a negative exponent. Also, since I have a square root, I need to have an exponent of 1 over 2. And that's all coming from this rule that says that the nth root of some number raised to the m, like this, is equal to a to the m over n. Now there's the extra thing happening here where ours is negative because the root is in the denominator. And there's also there's 2 other things going on here, which is that the notation is suppressed on the root and the 3. So technically, what's the exponent on the 3 here? It's technically a 1, right? We just don't explicitly write it. So that's where that 1 came from. And also for a square root, the index, the little n letter playing the role of n down here, is technically a 2 for a square root. We just don't write it. It's suppressed, right? It's a suppressed notation. So that's where the 2 is coming from. So with a square root of a number like this, literally both numbers that you need to worry about are not written. So you just kind of got to remember the square root, it's the letter n, like here, is not written. Its index is what it's called, is not written for a square root. So that's something to remember. So if I wrote this in a more helpful way, it would look like 1 over, there we go. And now it's got all that notation explicitly written there. Number 10 says cube root of 7 squared. Cube root of 7 squared. This one is more explicitly written, should be a bit easier. No need to worry about negatives because my 7 is not in a denominator. I'm going to have 7 raised to the 2 over 3. That index on the root should be the denominator over here. So 7, that's raised to the 2 over 3. Okay, let's see what else I got for this. Number 15, they give you the exponential and ask for the radical. So number 15 gives you over here. So all these problems like 9 through 19, there's like a big table with radical and exponential as the two columns. So 15 gives you a to the 2/5 and asks for the radical expression version of it. So you would say, you would draw a radical with a, right? And then the denominator should be the index over here. That's the number that gets stuffed right there. So that's a 5. That's a 5. So it's the 5th root of a, and then the 2 gets attached as an exponent to the a right there. And then just how about a little bit more practice with this section, because I know that it's tricky. Let me find another good one that just talks about simplifying radicals. Yeah, I wrote down 29. I don't think I want to do 29. All right, let's do it. 5th root of 32y to the 6th. All right, so the first thing you want to do here is decide how you're going to simplify the 5th root of 32, because we're going to do these in pieces, right? We know that we can split these two terms like this. So some number, is there some number such that when you multiply it by itself 5 times, you get 32? And the answer is yes. I would know the powers of 2. It is 2. I would know the powers of 2 up to like, I don't know, 8 or so. 2 to the first is 2. 2 squared is 4. They double each time, right? 2 cubed is 8. 2 to the 4th is 16. 2 to the 5th is 32. So that's what I'm looking for here. The 5th, if 2 to the 5th is 32, and I'm asking for the 5th root of 32, well, then that should just be 2. And then here, what happens is, this is an easier question. Basically, how many 5s fit into 6? Well, that's 1, so that means I could pull a y to the first power out. And then how many are left? Well, there would be one group of 5 with one little piece left over, so that stays under the radical. So there's 1 left under there, 1 y left under there. So then if I kind of clean this up, it would be 2y times the 5th root of y. So that's an example with simplifying radicals. I'm going to tell y'all there's a lot to do in 0.4, but I went easy on it. If you can do the problems, the first couple problems I did, just changing from rational exponent form to radical form and vice versa. So the first 3 I did here, 9, 10, and 15, then you're good. Because, I mean, I could literally give you an entire exam just based off of 0.4 because it's really expansive section. So I just focused in on just that one rule, basically this rule. All right, what else? Does anyone need the review problems? Didn't get them on Monday or whenever, I don't remember when I gave them out. But does anyone need them?
I was going to see if you would go over doing the finding the center and the radius again.
Yes, 1.2, right?
Yes.
So center and radius, so the circle given an equation. Yeah, I will do, so I gave you 71 from that section to review, that's the exact kind of problem that you're asking about. So I'm not going to do that one because I'll leave that one for you guys to try. I will do, what's an equivalent one? I'll do, no, not that one. I'll do, no, okay, well, none of them, 72. All right, I'll do 72. So we're finding center and radius of the circle. Let's say of the circle, and sketch its graph. Okay, 72 says x plus 1, x plus 1 all squared plus y plus 2 all squared is equal to 36. All right, I should immediately recognize this as the equation of a circle, and I don't need to like start squaring things or anything like that. I just need to recognize that this is the area of a circle. No, not area, my gosh, the equation of a circle on a graph. So I'm recalling the equation is like this, where basically those numbers inside the parentheses attached to the x and y describe the center. H comma k is the center. And I do need to flip their signs. So for me, the center here will be my center will be -1, -2, coming from the +1 and the +2 in my equation I was given. Okay, because the subtraction is built into the circle formula. So if you're saying addition inside the parentheses, you need to account for that by negating those values. Now in number 71, you'll see that one of the values is already being subtracted, so you do not need to flip its sign. But I have to flip both of these here. Oops. So let me reiterate that this is the center. Now my radius r is going to be, so it's equal to 36 is directly equal to r squared. So my radius is not 36, right? It's 6. It's the square root of 36. All right, so it's 6. Now, when I sketch this, okay, let's see. I'm going to need a fairly large graph just because it's a pretty big circle, radius 6. Okay, so that's 10, that's -10 down there. I'm not going as high that way. I know that my circle is centered in the down here where x and y are both negative, so I'm kind of going to make my third quadrant down here pretty big. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, there we go. There's -10. Okay. You won't have to worry about that. If you have to graph something on the exam, it'll be just like homework where they give you the graph, right? Like you don't have to draw it, right? You've got to draw the shape, but not the actual coordinate plane. All right, so my center is at -1, -2. So I'm finding that point. I'm finding that point -1, right there, -2. So there's my center. Now, how do I find those other points that are going to let me help me draw this? Well, remember, you take that radius and you go straight up, you go straight down, you go straight right, and you go straight left. And you find 4 more points, up, down, left, and right. By adding 6 or subtracting 6 to the x or y values. So to find the point to the right of this, I'm just going to go 6 this way. So I'm adding 6 to the x value. So I'm going 1, 2, 3, 4, 5, 6. That should be at the point, for, if I'm adding 6 to the x values, 5, -2. And it is, right? That's 5, -2. So I'll call that that's that point. Okay, just by adding 6 to the x value. Now, if I want to go straight up, I'll add 6 to the y value. So 1, 2, 3, 4, 5, 6. That point, if I'm adding 6 to the y value, it should be -1, the x doesn't change, comma 4. And that is exactly where that point is. Okay, now I'm going to go left. So I'll subtract 6 from the x value. So that means go left 6. So 1, 2, 3, 4, 5, 6. That should put me at, what would that point be? -7, comma -2, right? Subtracting 6 from -1 yields -7. Okay, and the y value stayed the same. And now down 6, so 1, 2, 3, 4, 5, 6. Putting me down here at -1 for x, comma -8 for the y value. And then you do your best to connect them all. So, and in WebAssign, you have like a little button that lets you draw the circle. Oh, that's pretty ugly, but you get kind of the idea there. So the point is, once you have the center and radius written down, to sketch a graph, you go from the center, you go 6 right, 6 up, 6 left, and 6 down. Okay, what else have you guys got? Okay. Make sure you're studying 1.5. The exam's going to lean a bit more towards that section just because there's a lot more to say about not just complex numbers and like how you can use, add or subtract, multiply them, or simplify radicals with them, but also the fact that they're complex solutions to quadratic equations, right? So make sure you're really studying that. Yeah. There's going to be about like a dozen questions on the exam. It's not going to be long. Okay, well, I will see you guys on Monday. I'll see everyone on Monday in person, except for Aviana. And we've already discussed what we'll do about that, so no problems there. You guys are good to go.